In this video, we're going to look at an application of Pascal's triangle called the binomial theorem. Now, let's say you want to expand x plus y to the power 6. Now, with our current knowledge, you can write that as x plus y times x plus y 6 times. That would take a long time to expand out. So what we're going to look at some smaller expansions first, but we're going to look at patterns that arise, and we're going to be able to apply Pascal's triangle to figure out a shortcut method. Now, what I have on the left-hand side here are expansions of x plus y to the power of 1, to the power of 2, and to the power of 3, done in the traditional ways. So you notice that it starts to get pretty long once we get to the power of 3. Now, over here on the right, I have the exact same final answers written out, but kind of in a different way. Basically, each term will have the x and the y variable each time. So the first expansion is simply x plus y, but I've written each term as having an x variable and a y variable. But because the y variable is not actually there for the first term, it will have an exponent of 0. And because the x variable is not really there on the second term, x will be to the power of 0. Now, I've also written in the exponents of x to the power of 1 and y to the power of 1. Normally, we wouldn't do that, but we're going to be looking for a pattern. What I also have written in here already are the coefficients are 1 and 1. Okay, now there's going to be a pattern with the coefficients and also with the exponents as we go to the next example. Now, x plus y squared expands to x squared plus 2xy plus y squared. So the first term would be 1x squared and then y to the power of 0 because y is not there. The middle term, though, has a coefficient of 2, x is to the power of 1, and y is to the power of 1. The last term is just y squared, so it's plus 1, x to the power of 0, y squared. Now, looking at the coefficients in red, you may start to see a pattern with this. But also looking at the exponents of each term, you may see a pattern as well. Now, the last one that I have here, x plus y to the power of 3. Now, this time I'm going to write in what the coefficients are. X cubed has a coefficient of 1. Then we have 3x squared y, 3xy squared, and then y cubed. So we have coefficients of 1, 3, 3, 1. Now, if I write in the exponents, the first term has x to the power of 3, and there's no y variable, so y to the power of 0. The next term is x squared, y to the power of 1. Then we have x to the power of 1, y squared, and finally x to the power of 0, y cubed. So let's talk about what's happening here. If you take a look at the coefficients, 1, 1, 1, 2, 1, 1, 3, 3, 1, that looks like Pascal's triangle, and that's exactly what the coefficients are doing. So to figure out x plus y to the power of 4, I'm going to fill out the coefficients because I know it follows Pascal's triangle. Now, the first and last coefficients will be 1. Looking at the previous row, 1 plus 3, this coefficient will be 4. 3 plus 3 is 6. 3 plus 1 is 4. So the coefficients are 1, 4, 6, 4, 1. And you notice that we can figure that out in one step now. Take a look at the exponents now. What's happening with the exponents? Well, let's look at just the x plus y to the power of 3 only. What's happening with the exponents on x? We start at x cubed, then go x squared, x to the power of 1, x to the power of 0. So the exponents on x are decreasing. What's happening to the y exponents? We start at 0 and then go 1, 2, 3. So as x decreases, y is increasing. And if you look at each pair of exponents, what do they add up to? They add up to 3, which is the exponent on our expansion. So basically, what's going to happen if we're expanding x plus y to the power of n? The coefficients will correspond to the nth row in Pascal's triangle. So row 4 in Pascal's triangle is used if we're expanding to the power of 4. The exponents on x decrease from n, so starting at whatever the exponent is on the expansion, and they decrease all the way to 0. The exponents on y increase from 0 to n, so from 0 all the way up to the highest exponent possible. So knowing that, now we can expand something like x plus y to the power 5 very quickly. Now, first thing I'm going to do is, well, it's x plus y to the power 5. I'm going to write out what the fifth row of Pascal's triangle is. And I can do that by looking at the previous row that we wrote out. So the coefficients will go 1, 5, 10, 10, 5, and 1. So notice how I separate them with addition signs. Now, beside each of these, I'm going to write my x and y variables. So x and y are multiplying each coefficient. And now I can write out what the exponents are. So because we're starting, it's x plus y to the power 5, I know that my exponents on x start at 5 and then go down to 0. So 5, 4, 3, 2, 1, 0. My exponents on y will start at 0 and go up 1, 2, 3, 4, 5. So there we go, and now I can just simplify it. So for proper mathematical form, we don't want coefficients of 1 or exponents of 0 or 1. So I'm going to write this out with proper form. And there it is. So I was able to do this in less than a minute. Now, they're not always going to be this quick to do. And the reason is we're just multiplying x times y each time. What if we had something like 2x? Or what if we had something like minus 3y? What would happen? Well, let's take a look. Now, the same pattern is going to happen, but it's going to be slightly different. So here we have an example, x minus 2 to the power 3. Now, I've expanded it out here in the traditional way, but what you'll notice is, well, the exponents now are 1, minus 6, plus 12, minus 8. Well, wait a minute, those aren't the coefficients in Pascal's triangle. What is this? Well, let's see what happens. Now, remember that last time we wrote x and y beside each other. That meant x times y. Well, this time the terms are x and negative 2. So for each of my pairs here, or each of my terms, I'm writing x and then times negative 2 beside it. X times negative 2. Now you'll notice that also the exponents are already filled in. So x is going from 3 to 0. Negative 2 is going from 0 to 1. Now I'm still going to fill out, because this is to the power of 3, I'm going to fill out the third row in Pascal's triangle, 1, 3, 3, 1. So what's different about this example here is that we actually have to expand out the exponents. Now, negative 2 to the power of 0 is simply 1. So the first term is going to be just x cubed. But here's where it gets different. We have 3 times x squared, then times, what's negative 2 to the power of 1? It's negative 2. Then 3 times x, and then negative 2 to the power of 2 is 4. That will multiply the 3x. And then we have, now x to the power of 0 is 1. Negative 2 to the power of 3 is negative 8. Now what I can do is I can multiply the terms that I need to. So 3 times x squared times negative 2 will actually give me minus 6x squared. 3x times 4 is plus 12x. And then adding negative 8 is just negative 8. So you can see that that's the same answer that we have in the full expansion. So the difference this time is we have to keep in mind order of operations. So we applied the exponents to that term, negative 2, each time, and then we can multiply together the coefficient and that term to fully simplify. Now I'm going to fill out the next one. I'm going to pause the video and fill it out, but I want you to take a look at it and understand where I got everything from. So very important about this one, it's to the power of 2. So the second row in Pascal's triangle is 1, 2, 1. Now, one of the terms here is 2x. Now, you just have to remember your exponent rules here. If we have 2x to the power of 2, that exponent applies to the 2. It also applies to the x. So that gives us 4x squared. A lot of people would just write that as 2x squared, but it's actually 4x squared. Now, over here, again, applying the exponents, 2x to the power of 1 is 2x, negative 1 to the power of 1 is negative 1, and again, all three of those are going to multiply each other eventually. And then lastly, we just have, now 2x to the power of 0 is 1, so negative 1 squared is 1, And now I can simplify, again, simplify that middle term right there by multiplying 2 times 2x times negative 1 is minus 4x, and that matches what we have over on the left. So very important, we're going to show 3 steps. Our first step is going to be writing out the pattern using Pascal's triangle and the idea of the binomial theorem. Our second step is we apply the exponents. The last step, we can do any multiplication that needs to happen. Okay, so just remember order of operations with that. You have to apply the exponents first and then multiply. So I'm going to do this first example with you, and then I'm just going to include the last example in the document, so you're going to have to read that over yourselves and take a look at it. Now I see here that we have 3x minus 4 to the power of 5. So first thing I'm going to do is write out the 5th row in Pascal's triangle. Now the next thing I'm going to do is I'm going to write out each of the terms, so 3x and negative 4, multiplying each coefficient. Very important that you write it as multiplication. A lot of people will write 3x minus 4 like this, and that's not quite what we want to do. It's the two terms multiplying each other. Now I can write out the exponents. So I know the first term, 3x, will start with an exponent of 5, and then go down 4, 3, 2, 1, 0. The second term, negative 4, will start at 0 and go up 1, 2, 3, 4, 5. Now each pair of exponents adds to 5, so I know I'm on the right track. Now what I'm going to do, I'm going to apply the exponents to each of these. Now very important again, 3x to the power of 5, both the 3 and the x get the exponent, so that'll be 243 x to the power of 5. Negative 4 to the power of 0 is 1. Plus 5, now 3 to the power of 4 is 81 x to the power of 4. And then that will multiply by negative 4, because negative 4 to the power of 1. So now I'm going to pause it and fill out the rest of the exponents. All right, so I've applied all the exponents. Now I kind of ran out of room there, so my last term is just below. That's okay if that happens, because these things can get pretty long. My last step to fully simplify, now I'm going to take a look at each term, and I'm going to multiply it out. So 5 times 81 times negative 4 will be minus 1,620 x to the power of 4. The next one, 10 times 27 times 16, and those are all positive, is plus 4,320 x to the power of 3. All right, so now again I'm going to pause it, fill out the rest. All right, so there's our full solution. So when we're doing these problems, it's always going to be a 3-step process. Very important that we show our 3 steps. The first step is just understanding what the pattern is going to be, so filling out the coefficients and the exponents. Our second step, we apply the exponents. Last step, we can multiply the coefficients to simplify, but please only do that in the last step. Don't try to rush and show that in the second step. Now I'm going to fill out the second question on my own, so make sure you check it out in the attached document.